To combat red light running crashes, many states are adopting photo red enforcement programs. In these programs, red light cameras installed at dangerous intersections photograph the license plates of vehicles that run the red light. How effective is this? The Virginia Department of Transportation conducted a comprehensive study in June 2007. The data, measured as the number of crashes caused by red light running per intersection per year for 13 intersections in Fairfax County, is in the table. Analyze this data. Run a hypothesis test to determine if installing the camera helps. Conduct a 95% confidence interval and interpret it. And we're using alpha equal to 0.05, our level of significance. So if we look at this table, we have 13 intersections in our sample. Of course, there are many more intersections in Fairfax, but this is just 13 of them that the study was done on. What was the number of crashes per intersection per year before the camera? We can see in intersection 1, it had 3.6 crashes per year. So that may be an average per year before the camera was installed. And then when the camera was installed, it was averaging 1.36 crashes per year. Notice intersection 2, it averaged 0.27 crashes per year. And then maybe it's because that intersection might not have been as busy. It averaged 0 per year after the camera was installed. So we go down the list there and we've collected this data. Now, this is a case that we could apply matched sampling to. Instead of thinking of this as two populations before and after the camera was installed, we can think of this as just one population of intersections, all the intersections in Fairfax County, and we have a sample of 13 of them. We can take a measurement on each intersection where we calculate the number of crashes per year before the camera was installed, subtract the number of crashes per year after the camera was installed. And that difference will be our measurement. So my measurement on these intersections is taking the before value, subtract the after value. Now I'm going to define mu sub d equal to population mean difference between the number of crashes per year before the camera was installed and after the camera was installed for all intersections in Fairfax County. So mu sub d is the population mean difference between the number of crashes per year before the camera was installed and after the camera was installed for all intersections in Fairfax County. Now, we have a sample of 13 intersections in which we have collected data on. To estimate mu sub d, I want to calculate d bar, and that is the sample mean difference. And to get the sample mean difference, I have to get the differences. So what I'm going to do is I'm going to select all of the data in this table, open up Excel, paste my data into Excel, and then to get the differences, I'm taking before, subtract after. So let me just write that as B subtract A. And then I'm going to select the first cell there. I want to take the 3.6, subtract the 1.36, and then I want to take the 0.27, subtract the 0, the 0.29, subtract the 0, the 4.55, subtract the 1.79. I want to find all these differences. So I'm selecting the very first intersection over here under in this column, and I'm going to go up to the function window here, and I'm going to type in an equal sign. That will tell Excel that what I want to insert into this cell is a formula. And then I just tell Excel what I want to do. So if I select the before camera value, notice that's in location column B, row 2. And then I'm going to hit subtraction on my keypad, and I want to subtract the corresponding value in column C, and that's all I want to do. I want to find that difference, so I'm going to hit enter, and there's the difference between the two. Now, if I reselect that cell and then go down here into the lower right corner, you'll notice that the cursor changes to a plus sign. I'm going to click and drag down to the bottom, and it will find all the differences for me. Now, that's the set of sample differences. And what I want to do is to go up, and I'm going to select Data Analysis, and I want to do Descriptive Statistics. That'll give me everything. And I want to find descriptive statistics on my difference data. So I select all my data. Notice that I didn't select the column label B minus A. I could have, but I didn't, so I'm not going to check labels in the first row. And then I want to go down to output range, and I want my output with this is the upper left corner, and I'm going to check summary statistics. So hitting OK. Now to read that, I'm going to notice I'm going to move the cursor between the two here and open it up a little bit. And I get my data. My D bar is 1.0069. This value right here is my S sub D, standard deviation of the differences. And then my count here is 13. That'll be my N sub D. Okay, I think that's all the information we need from that. So I'm going to round D bar as 1.007, and I'll use 1.209 for my standard deviation, and then 13 for my difference data. So D bar is 1.007. The standard deviation of the difference is 1.209. And then my sample size, N sub D, is I have 13 differences. To estimate mu sub D, I've got a positive. Notice that that is a positive 1.007 from my sample. Now, what does the positive mean? As we've seen before, that's going to depend on how you subtract it. So it appears that the average difference is 1, reducing the number of crashes per intersection per year by 1 crash on average, the differences. And this is an estimate because it's from a sample. What I would like to prove is that the camera helps. So to do that, I would try to prove that mu sub D is greater than 0, right? Mu sub D is the mean difference, and that difference is being calculated by taking before, subtract after. If that value is positive, that means that the number of crashes before was greater than the number of crashes after. And that's what I would like to prove, to show that the camera helps, that it reduces the number of crashes. But again, by the way I subtracted, that would be a positive mu sub D. And then what will I assume? I will assume that mu sub D is less than or equal to 0, or as we normally do, we'll just put equal to 0. Okay, that would be step 1. And step 2, notice that this is just one population. So this goes back to chapter 7. I'm assuming that the null hypothesis is true, so that there is no difference. The camera doesn't change anything. And my standard deviation would be S sub D over the square root of N sub D. So I'd have 1.209 divided by the square root of 13. And that would be equal to 0.3353. This is going to be an upper tail test, and it's going to be a t-distribution. I have a sample standard deviation, and my sample size is small, so I'm going to go with the t-distribution here. I'm assuming all the other conditions are met to do that. My T alpha value, this is a one-tailed test, so this would be T.05. And my degrees of freedom for this value would be just n sub d minus 1, which in my case would be 12. So I have 13 data values, subtract 1, be equal to 12. Now let's go to the t-table, and I have 12 degrees of freedom, and t sub 0.05, so 1.782 would be my value. So 1.782. Now I have my rejection region, so I'm going to say reject h sub 0 if t is greater than or equal to 1.782. And t being my test statistic, I would take my sample mean, subtract what I'm testing against, divided by the standard error. And this calculates out to be 3.003. And I can now conclude I can reject h sub 0 since 3.003 is greater than 1.782. I can conclude the camera helps reduce the number of crashes. Now, in a sense, I'm done. I've proven that the camera helps based on the sample data. It was strong enough evidence that I could reject the null. Now, what about the p-value? I want to calculate a p-value. Now, the 1.007 is way out here on the upper end of this interval. And why do I know that? Because it is 3.003 standard deviations to the right. So I got to go a little further out on this distribution to see where that's at. The level of significance is 0.05, so that is the probability of being greater than where our decision line is. In other words, it's the probability that the sample average would be greater than where our decision line is. And so that is 0.05 probability. The p-value is the probability of being greater than the 1.07. So it's out here on the upper end. It's the probability of getting a sample average greater than 1.007. Or you could think of it as the probability of getting anything less likely than what you got with the 1.007, given that the null hypothesis is true. And to calculate it, we can either use the table or go to Excel. But if I go to the t-table, remember I'm at 12 degrees of freedom. Where's the 3.003? It's right between these two values, right? So it's somewhere between. The only thing the table can tell me is that my p-value is going to be greater than 0.005 and less than 0.01. Regardless of where it is between those two values, I can say that the p-value is less than 0.05. So again, I would of course come to the same conclusion as I did using the rejection region. But I would reject h sub 0 in this case. Let's go back and use Excel to calculate the p-value and get a more accurate value. I'm just going to click a cell, and then I'm going to go up to the function menu, go down to statistical, and I want a t-distribution right tail. So t.dist.rt. And my x value will be 3.003. And my degrees of freedom will be 12. 13 subtract 1. And I get 0.0055. So the p-value is 0.0055, and that is less than 0.05, so reject h sub 0.